What's up? 3, 2, 1. What's up, guys, and welcome to this tutorial on question 7 of the 2016 supplementary exam. This question deals with electric circuits and it's worth 28 marks. Okay, cool stuff. So let's go over it. Okay, so question 7.1 says a battery powers a torch that has a bulb with a resistance R is equal to 6 ohms. The potential difference across the bulb V is equal to 3 volts. Okay, so question 7.1.1 is a definition, and it says define potential difference. Okay, I'm actually going to do the definition above. 7.1.1 says define potential difference. Okay, so potential difference is the work done per unit positive charge. Okay, and that's the definition, and we get 2 marks for that. Okay, so question 7.1.2 says calculate the current in the bulb. Okay, so that's quite simple. We use the equation V equals IR. V was given to us as 3 volts is equal to I, which is the unknown because we're looking for the current, times the resistance, which was 6 ohms. I is the only unknown here, so we can solve for I is equal to 0.5 units of amps. Cool stuff. Question 7.1.3 says calculate the amount of charge Q that passes through the bulb in 10 minutes. Okay, so let's see. If we look at our formula sheet and we look for Q, okay, first equation, actually I equals Q over T. So I is equal to Q divided by T. Okay, I we just calculated as 0.5 is equal to Q, which is the unknown, times T in seconds. Remember, time is in seconds, so that's going to be 10 minutes times 60 seconds. Okay, the only unknown here is Q, so we can solve for Q, and we can say it is equal to 300 units of coulombs. Then we get 3 marks. Okay, so that's 368 marks right there. Okay, so question 7.2. The circuit illustrated was set up by a group of students. The EMF of the battery was 12 volts. So the EMF equals 12 volts. When the switch S is closed, the ammeter reads 2 amps, which is shown, and the voltmeter reads 10 volts. Okay, that means that the voltmeter here also reads 10 volts, and the voltmeter across this branch also reads 10 volts. I'm also going to write that our V, our voltage loss, is 2 volts. That might come in handy later. Okay, so question 7.21 is once again a definition for EMF. Let's see. Okay, so the EMF is the total energy per coulomb of charge supplied by the cell. Okay, so that's the EMF. Okay, 7.2.2 says calculate the internal resistance of the battery. Okay, so I'm going to use the method that the voltage loss is equal to I, the current, through that main battery, which is highlighted in green, times the R, small r, which is the internal resistance. Okay, so the voltage loss I already said is 2 volts, and I got that by just saying voltage loss is equal to the 12 volts minus the 10 volts. Okay, so equals to 2 volts. Okay, so 2 volts is equal to I, which is the current, which is also 2, times the internal resistance. The internal resistance R is the only unknown there, so we can say R is equal to 1 ohm. Okay, we could also use the equation that the voltage is equal to the EMF minus IR, which is exactly what I did, except I calculated the voltage loss first, which is what we do in this part of that equation. Okay. Okay, so we get 3 marks for that too. Okay, question 7.2.3. Calculate the current in the 20 ohm resistor. Okay, nice and simple once again. This value here is 10 volts. So V, we can use the equation V equals I times R. The voltage is 10 volts is equal to I, which is the unknown, times the resistance of 20 ohms. The only unknown here is I, so we can solve for I is equal to, once again, 0.5 amps. Very nice. And we get 3 marks for that too. It's a bit generous, I think, but nevertheless, we can be happy. Okay, question 7.2.4. Okay, so the power dissipated by a resistor labeled R1, so power is equal to 5.85 watts, the dissipation. Determine the resistance of the resistor labeled R1. So find R1 basically. Okay, so what information do we know? We know that the current here is 2 amps. We know that the current here is 0.5 amps. Okay, so I'm going to use the equation P. Okay, so there's 3 options here. We have power equals voltage times current, or power equals I squared R, or power equals V squared over R. Okay, so I don't know what the voltage across R1 is. R1 alone. That's an unknown voltage. So I'm going to leave that and try and work out the current. Okay, and using Kirchhoff's current law, we can say that the sum of the currents, or we can say that the current in, let's label this I0, is equal to I1, I2. So I0 equals I1 plus I2. So I0 is 2 is equal to I1, which is 0.5, plus I2. So we can say that I2 was calculated as 1,5 amps. So the current through this part of the circuit is 1,5 amps. Okay, so knowing that, okay, we're going to have to show, okay, so we should have shown that here, but I already showed it up there, so I'm just going to say I2 equals 1,5 amps. So we can use the equation P equals I squared R. So we know the power that was given is equal to, let's see, when we just calculated the current, 1.5 squared R1. Okay, so the only unknown here is R1, so we can solve for R1, which is equal to 2,6 units of ohms. And we get 4 marks, which is fair enough. Okay, now it says determine the resistance of R2. Okay, so R2. How are we going to do this? Okay, so first what we're going to do, okay, so now we know the current. We know the current through I1, so we can work out, let's say this is V1, and this here is V2. Okay, so we know that V1 plus V2 is equal to 10 volts. Okay, so if we figure out V1, we can figure out V2, and then we can work with V2. So that's the plan of action. So if to calculate V1 equals I2 R1 plus V2 equals 10 volts. I'm going to leave out the units actually. So we can say that I2 we calculate as 1.5 times R1 is 2,6 plus V2 equals 10. So if we carry that out, the only unknown here is V2. So we can say that V2 is equal to 3,9 volts. Okay, 3,9 volts. Now it's just a simple V2 equals I2 R2. V2 we calculate as 3.9 equals I. Sorry, this is a mistake. Let me just fix this as well. Sorry, V1, this calculation right here is equal to 3.9. So V2 is actually equal to 10 minus that, which is 6.1. 6.1 volts. Okay, so correction was made here. 6.1 volts. Okay, again 6.1 volts is V2. Okay, but everything else still stands. So V2 is 6.1. Okay, I we calculated as 1.5, and R2, the only unknown here is R2, so we can solve for R2. R2 is equal to 4.07 ohms. Okie dokie, and we get 4 marks for that. Okay, then we move on to 7.2.6. Okay, question 7.2 says, will the reading of the voltmeter across the battery increase, decrease, or stay the same when S is open? Use equations to explain. Okay, so when S is open, okay, let's clean this up. Let's get rid of that, get rid of stuff that I don't think is important. Okay, so when S is opened, so we open that. So what happens is we only have a series circuit now, right? So our resistance is going to go up. So when S is open, the resistance increases. Okay, so if the resistance increases using V equals IR, if the resistance increases, so we can say therefore the current through the battery goes down or decreases. Okay, and we can even say using V equals IR. Okay, so that's, well, we don't actually have to say that. Let's leave that part out because that would require us making a little equivalent circuit. Yeah, okay, so we know that I has now gone down. Okay, now we can use the equation by using V is equal to the EMF minus IR. Okay, so the EMF is the same, so this has to stay the same, EMF stays the same, small resistance stays the same, but I goes down, right? So if I goes down, then voltage would increase because now we are decreasing the EMF less, if that makes sense. So I goes down, so if let's say the EMF, we know the EMF was 12, so initially it was 12 minus 10, but now the current's gone down, so the new one is something like 12 minus 8. Okay, so initially we had 2, and now we have 4, if we just put a scenario to it. Okay, but let's take that out. So we can say therefore V will increase. Yeah, okay, I'm happy with that, and that is 28 marks. 28 marks in approximately, let's say, 15 minutes, which is not bad. Yeah, so very nice question, interesting and quite straightforward. Okay, so thanks for watching, guys. I hope you found this useful.